Okay, thank you. So as Grace mentioned in the introduction, increasingly software systems are composed at runtime. If you think services, microservices, cloud-based systems, a lot of the design is in fact not established until runtime. But there's been very little research on the impact of runtime composition on the quality of software systems. We do have a lot of experience with static analysis of software systems. And this experience has shown us that there's a very strong correlation between design flaws and bugs, security vulnerabilities, changes, churn, the effort to fix bugs. But the static analysis, of course, does not currently detect the consequences of dynamic composition. Whoops. So the solution that we were striving for in this lens was a technique to detect design flaws that were introduced dynamically, introduced at runtime, either fully automatically or semi-automatically. So our challenges were, first of all, just to detect these dynamic dependencies at all. It turns out this is a non-trivial problem, that there are many ways in which one component can dynamically interact with another component, and many mechanisms through which they do so. Then, assuming we can do that, our next challenge is to determine whether these dynamic dependencies create new kinds of design flaws, introduce new kinds of errors into the composed system. And what are the consequences of these design flaws? What do we have to do to mitigate them, address them, fix them? And finally, and this goes beyond the scope of this lens, but of course, once we've determined these design flaws, we'd like to propose refactorings to actually address them, to fix them. So we did two things in this lens to attempt to address this problem. The first was in collaboration with David Garland's group on campus. And what we did was looked at extracting dynamic dependencies from Android applications or Android suites, which communicate with each other dynamically through intents. So we had a model extractor, which was a static fact extractor, which we then were able to translate into ACME, which is their architecture description language. This gave us a recovered system architecture, which was describing the extracted information in terms of first-order predicate logic. And then we could do a conformance analysis. Essentially, we could look at the predicates that were produced and look for whether certain conditions hold among those predicates. So for example, we could look at the data flows between components, and we could determine whether there were violations of information disclosure properties among those components. So we want to determine whether it's possible for one app to communicate information to another app that has a lower trust level. In addition, we were able to convert these first-order predicate logic representations of the recovered system into Alloy, a formal language, which again is first-order predicate logic, and we could feed this into Covert, which is a model checker, and this allowed us to check additional properties of the system. So we could check, for example, privilege escalation properties of the system. However, this approach, it turned out, was not particularly scalable. It didn't scale to other kinds of mechanisms, other kinds of languages, or even size of application very easily. So we turned to another approach, which was trying to discover dynamic dependencies through tracking issues. So the idea is that if two components have a dependency relationship on each other at runtime, you will often see co-change relationships between these components if you look at the issue tracker, if you look at the revision history of the project. So what we did was we mined issue tracking systems, issue repositories, and revision control systems to discover these quote-unquote hidden relationships. And we could use that information to determine these, not only the additional relationships, but whether these relationships introduce new kinds of design flaws among these related files. So to do this, we created a new kind of architectural view that we call an issue space. And an issue space consisted of a series of snapshots of a system, essentially a series of commits over time, n commits representing the number of changes to that set of files in the revision history. So each snapshot consists of a graph, basically a representation of the elements involved and their relationship, and a timestamp when the commit is made to address the issue. And so as an example, let's get concrete. Here's an example that we analyzed from Apache Cassandra, which is a well-known distributed scalable database, quite prominent. And here's issue 436. The initial commit involved a change to one file. This commit was found to not actually resolve the issue. And so later on, there was a second commit which involved an additional 7 files. And you can see from the design structure matrix representation of these now 8 files that there were a lot of dependencies between these files that we could discover. So these files are related. They're dependent on each other. But it didn't end there. There was a third commit and finally a fourth commit before the issue was actually completely resolved. In this fourth commit, we actually had 13 files, and many of these files are dependent on each other. It's not a fully connected graph, but it's pretty close. Okay, so what are the consequences of discovering these relationships by looking at issues? Well, one of the things that we've shown is that when we find these files, what we call hot files, files that are changed in response to many different issues, that they're actually related to each other. These files are related to each other, and so we call this a hotspot. And these hotspots have design flaws. They have structural flaws. And those flaws lead with very high correlation to bugs, security vulnerabilities, and high cost, high rates of changes, a lot of effort to fix these bugs. Hence, this is a mechanism that allows us to isolate and identify these areas that should be analyzed and refactored. So again, looking back at Apache Cassandra at issue 436, here's a design flaw where you can see that SS table scanner depends on SS table reader, and SS table reader depends on SS table scanner. There's a cyclic dependency between these two files, high coupling, always a bad thing, and this in fact did result in lots of bugs such as the issue 436. Here's another example from a different open source project, Apache Pig, and here we see a different kind of design flaw. This is a modularity violation. So in this case, there were 2 files that changed very frequently with each other according to the revision history of the project, but there was no structural dependency. There was nothing that you could detect in a static sense as a relationship between those 2 files. And so there's some information that ought to have been modularized and encapsulated in an interface, but which was not, and hence a design flaw. Okay, so where are we now? Well, first of all, to conclude, the good news is that by considering dynamic information, we can in fact find design flaws, and design flaws that are not detectable by static information solely. And this allows us to determine the root causes of bugs, the design causes of bugs, much more quickly. So we need to discover and employ dynamic information to really understand the design consequences of decisions that are being made in systems. And again, this is the root of technical debt. These design flaws are causing enormous amounts of bugs and effort in these systems. And so in our future work, in a lens that has just begun, we're now looking at the relationship between these design flaws and security bugs in particular. With that, I'm happy to take any questions. I think I have about 1 minute.
Okay, so I know that there's been talk about use of ADL. We're talking of modeling and analysis of our software system. Is it possible for us to look at these dependencies? We're working on something within the Army. It's called Joint Common Architecture, where we're trying to take mission-level capabilities, low-level capabilities, eventually create software components out of that. So the dependencies that you're talking about here, dynamic dependencies, is it possible for us to do modeling and analysis of this with your approach? I don't know how familiar you are with the OSATE and the ADL.
Sure, yeah, no, I am familiar with it. And yes, absolutely, it's possible. The challenge is getting the information into an AADL representation in the first place. The reverse engineering allows you to obtain some of those relationships, some of the information that would populate an AADL specification. But kind of the point of this lens was there's a lot of other information that you can't get just by reverse engineering a system, and we need that information to get a complete picture of the dependencies in the system. Without that, you really just have one eye open.